Thank you for inviting me to speak. Right, so I want to tell you about some recent, let's get a highlighter, some recent joint work with Mike Mandel and Alan Wan. And this is about chromatic convergence for K of S, and in particular about an old conjecture of Waldhausen about chromatic convergence of the K theory of the sphere spectrum. So just to set the stage for this a little bit, a basic question in algebraic K theory is to understand the K theory of the sphere spectrum. The sphere spectrum is the initial E infinity ring, and there are lots of reasons to want to know what its algebraic K theory is. One kind of reason is that for any suitable category, by which I mean essentially for any category you can take algebraic K theory of, if you start with C, K of C is going to be a K of S module. So K of S gives you the operations on K of C. And another sort of more high-tech way of saying that is that if you think about the perspective that algebraic K theory is co-represented by some sort of object in a category of non-commutative motives, then K of S is the spectrum of endomorphisms of the unit. And, and this is true, there are a variety of perspectives on analogs of this sort of non-commutative motives approach to K theory, notably work of Clark Barwick or work that I did with David Gepner and Gonzalo Taboada. And there's sort of lots of variants of this, but in any of them, K of S is a distinguished object of importance. There's also the classical picture, which is maybe why Waldhausen invented K of S, which is that, the big theorem that Waldhausen's algebraic K theory work, at least in the kind of direction that led to the definitions that we use now, more or less, was trying to understand a relationship between the K theory of what you might think of as the spherical group ring. Maybe it's nice to sometimes write this like this. The spherical group ring of a manifold, of the based loops on a manifold, and what's called stable pseudo-isotopy theory. And there had been work in sort of geometric topology of Hatcher and Agusin, though most notably, showing that if you stabilize the pseudo-isotopy functor or concordances or something like this, then what you get, and stabilization here means crossing with intervals, then what you get is a homotopy functor. And that homotopy functor turns out to have an algebraic description in terms of the K theory, the Waldhausen's A theory, which is the K theory of spaces. But by the usual picture, we can think of that, equivalently as sort of parameterized spaces or as modules over the based loop space. And so what this tells you in this specific case, when M is a point, what this tells you is that the K theory of the sphere spectrum is related to B diff for high dimensional disks, some kind of stabilized B diff information. So there is this relationship, or K of S is some kind of locus where there's a connection between invariants of geometric topology and algebraic invariants, which, as we'll see, are related to, we'll see, maybe I'll assert, and maybe are also related to questions of arithmetic. Now, this, just to say a little bit more about the history of this is a vast generalization, a sort of parameterized generalization of the S-cobordism theorem, which tells you that, the H-cobordism theorem tells you that if you're in dimensions 5 and above and you are simply connected, then, then any H-cobordism is trivial. And the S-cobordism says if you drop the simply connected assumption, you have an obstruction, and that obstruction lives in what's called the Whitehead group, which is very closely related to the K theory of the integral group ring of pi 1. I guess I wrote X here, and maybe I meant M. Let me fix that for consistency. Okay, trying again. There we go. So this and the K theory of the spherical group ring, of course, is a spectrum level lifting of the integral group ring. So Waldhausen proposed, really quite a long time ago, that we should understand. So how can we think about K of S? It's hard to compute. It's hard to compute the algebraic K theory of anything directly. And at the time that Waldhausen was working on this, there was only sort of the beginnings of a hint of the existence of trace methods. And the Quillen-Lichtenbaum conjecture hadn't been resolved yet. And so we really had very few tools. And he proposed, however, that we understand K of S in terms of the chromatic filtration, where he made the following conjecture, which I would refer to as Waldhausen's chromatic convergence for K theory conjecture. And what it says is that the K theory of the sphere spectrum should be the inverse limit of the K theory of the finite chromatic localizations of the sphere spectrum, where here by LNF, I mean the finite telescopic localization. And Waldhausen was motivated. So when he made this conjecture, he was motivated. I think he had learned about recently the Hopkins-Ravenel chromatic convergence theorem, and in general, sort of the Ravenel conjectures and the, and then the nilpotence theorem work of Hopkins and Devenantz and Smith. And this tells you, so what is the chromatic convergence theorem? In the case of the sphere, it tells you something like the p-local sphere is the Wholem-Homotopy limit of the, chromatic localizations, LNS. But when this was done, it was a time of great optimism about the telescope conjecture. Or, I guess I can't speak for everyone, but I should say that Waldhausen in his writings on the matter expresses great optimism about the telescope conjecture. And so he thought that LNF and LN were the same. And so sometimes this is stated in terms of LN, but if you look at what he actually does, he's working with LNF. And so he thought that this was true as a consequence of what had been proved, and then made the conjecture. Now, we live in a more skeptical era. And so given sort of general skepticism about the truth of the telescope conjecture, what do we really know? What we know is that the map, the chromatic completion map, if you will, from the sphere spectrum to its chromatic inverse limit, factors through the finite completion tower, this inverse limit of finite localizations. And another way of saying this is that S is a wedge summand of that thing. That's what we know. And in light of this, I think one could argue, maybe I will argue, that sort of a reasonable reformulation of Waldhausen's conjecture is to make the conjecture that, that the K theory of the sphere spectrum, the p-local sphere, is a wedge summand of the homotopy limit of the K theory of the finite telescopic localizations of the sphere. And so the goal of this talk, what I want to do, is explain the proof of this conjecture. So this is now a theorem, and at least localized at P. And the key ingredient, it's an interesting thing that one of the key, there's sort of two key ingredients in the proof, and one of the key ingredients is a chromatic convergence result for K theory, namely that the K theory of the sphere spectrum, if you pass to the connective cover of the chromatic completion of the K theory, so we have sort of two different kinds of chromatic completion happening. In these conjectures, we are taking the limit of the localization on the inside. But if you look at the localization on the outside, which is what comes up in the statement of the chromatic convergence theorem for p-local spectra, then on connective covers, K theory is chromatically convergent. And moreover, in general, we can identify the homotopy fiber of the map from K of S to this homotopy limit in terms of a shift of the Anderson dual of the K theory of the integers. And sort of the a broad slogan is that K theory is chromatically convergent. K of S, sorry, is chromatically convergent. And before, so I'm going to try to explain an overview of how this proof works. But before I do that, I want to offer some perspective on this. And what I want to suggest is that we think about we want to think about this as a kind of Quillen-Lichtenbaum statement. And yes.
Sorry to interrupt. You have a question in chat.
Yes. Sorry, the question in the chat.
So the question is...
Yes, it's a K-theory of the integers. That's right. So we want to think of this as a, I apologize. I tried to be careful about where I'm p-completing, but if I wasn't, then you can't figure it out. Please let me know. So we want to think of this as a kind of Quillen-Lichtenbaum theorem. And Waldhausen, using ideas or building on ideas of Thomason and Snaith, showed that the Quillen-Lichtenbaum conjecture, the classical one, is equivalent to essentially to the statement that the map from K of Z to, at least for Z, to L1 K of Z, or more generally K of a ring of integers to L1 of the K of ring of integers, is an equivalence in high degree. And really is an equivalence, I think above 0 and 1 or 0. And Mitchell's result about the interaction of K-theory and chromatic localization shows that in fact L1K, the natural map L1K of Z, and maybe that map goes the other way, comparing that to the homotopy limit of LNK of Z is an equivalence. So this, so the Quillen-Lichtenbaum conjecture for K of Z is something like a convergence result, a chromatic completion convergence result of this kind. And now, there's been an enormous amount of really great work recently on higher height analogs of the Quillen-Lichtenbaum conjecture, stemming from proposals of Rognus that now get referred to as the redshift program, or the redshift conjectures. And suitably distilled, these say something like, or they ask questions about whether the map from K of R to LNF K of R for suitable R is an equivalence if you take a high enough cover. And to give a, I hope, relatively complete, but if I left you out, I apologize and you should let me know, summary of people who have done nice things with this. Of course, there's original work of Alsoni and Rognus. There's work of Angelini, Knoll, and in some cases with Quigley. There's work of Carmeli, Schlenk, and Janowski. There's this descent work of Clausen, Matthew, Naumann, Knoll. There's recent work on, very nice work on BP brackets N by Han Wilson. There's the purity work of Land, Matthew, Meyer, Tam, about which more will be said slightly. And Alan Wan has a nice perspective on this, which I think is which he's been talking about and which is supposed to come out real soon now. So the observation, and this now follows from this considerations in this purity work, is that this statement is essentially equivalent to asking that K of R have a chromatic convergence result for the finite localizations. This is some sort of equivalence on highly connective covers, and that that the higher Morava K-theory localizations of the input ring are 0 above N. And what this suggests is that we can drop this height restriction, and this leads to an infinite height analog of the Quillen-Lichtenbaum conjecture, where you simply focus on the question of whether or not the map from K of R to the telescopic chromatic completion of K of R is an equivalence after suitable connective covers. And you can ask this question for, now you can ask this for infinite height ring spectra, in particular for the sphere spectrum, which in some sense is the subject of discussion today. And also, I would be personally very interested in understanding what this kind of thing meant for MU, about which I have no idea, or maybe not no idea, but very limited and fragmentary ideas. And I think we would choose to refer to this as a question about telescopic semi-convergence, just as terminology. Okay, so now let's assume the chromatic convergence result for K of S. So that means, let me just go back up. Let's assume this business, maybe we'll make this red. Let's assume this stuff. Okay, we've identified the chromatic completion of the K-theory of the sphere spectrum. So now, how does the proof go? So the other main ingredient of the setup is that by the work of Land, Matthew, Meyer, and Tam, we know that the natural map from the Wholem of ln of k, and this is the chromatic ln of k of s of p, to the Wholem of the chromatic localization of ln of f on the inside, that this map is an equivalence. Okay, I mean, they prove much stronger things. But this is a consequence of what they prove, because, the map from SP to LNF SP, LNF S is, suitably suitable telescopic equivalence. And so what we do is that if you completed P, this gives us a map where we start with the K theory of the sphere spectrum, we go to the K theory of the telescopic completion on the inside, we go to the chromatic completion on the outside, and now the inverse of this map takes us back to the chromatic completion of K of S, and that's by previous discussion on connective covers is equivalent to K of S. And we can identify this as the chromatic completion map. Now we also have, that's at P, we also have rational maps from the rationalization of the K of S to the rationalization of the chromatic completion of K of S, which factor through this telescopic completion on the inside. And the point here basically is that these are all the natural maps, and the splitting here comes from the fact that the map from K of S to K of Q rationally is basically an equivalence, I think, except on pi 1, and you can shoot but we know what pi 1 is, and you can choose an explicit splitting. Okay, and the work of proving the theorem, once you have this set up, the work of proving the theorem is primarily to show that first, that these maps are compatible with the arithmetic square. And this is tricky. I mean, or, I don't know. We found it tricky. Maybe you will find it easy, but we found this tricky, and I'll make a comment about that trickiness maybe at the end. But you can, you have to do some work to patch these things together, and then you also have to assemble this stuff just to show that this actually factors through in the homotopy category. Not this, that this composite factors through in the homotopy category K of S. And so what we get is a map from K of S to this completion back to K of S, which actually is the identity, or can be chosen to be the identity in the homotopy category. And that gives us our splitting. So the setup is not so bad. The details require a bunch of work. And one of the interesting parts of the details is that although what we are concerned with, K of S is connective, and what we're concerned with is a statement about connective stuff, understanding the compatibility, the required compatibility arguments actually requires that we understand the, oops, I did this wrong. This should be, sorry, there we go. Understanding this as a non-connective spectrum. So we really do need to know what that fiber in negative degrees is. At least the way we did the argument. I guess I can't prove that that's absolutely required. Okay, so let's now talk about that part. So how do we understand this thing? This is this chromatic completion of K of S. And of course, what do we always do? The key tool is the Dundas-McCarthy-Goodwillie square, right? So you know that you have this homotopy Cartesian square where these maps are the linearization maps, these maps are the cyclotomic trace. And this being Cartesian implies that basically the question of whether K of S is chromatically convergent reduces to the questions about for K of Z, TC of Z, and TC of S. And well, work of Hessel, Holt, and Madsen fairly early on about understanding, computations of TC of Z and K of Z and things like this establishes, this is a Wholem-Lichtenbaum statement, and establishes the required statements for these things. I guess the Wholem-Lichtenbaum conjecture for this and their work for this. And so it boils down to understanding TC of S. But TC of S is pretty easy because we know what TC of S is. I guess this statement is only after P completion. But what it's the wedge of the sphere spectrum, which is convergent, and CP infinity minus 1, which is the fiber of the S1 transfer from B of T, from B of S1 to the sphere spectrum, and the sort of souped up version of the chromatic convergence theorem due to Toby Bartle tells us that also has chromatic convergence just by a BB homology calculation. So this is pretty easy. Now, one thing that's in the background here, and that I'll say more about in just a second, of course, is that in previous work, Mike Mandel and I computed more or less what the homotopy groups of K of S are. And if you look at the homotopy, from this square, but if you look at them, it's very clear that it should converge because they break into pieces that work. And say one more thing about what's happening here. It's kind of interesting, and this, this square, what this is telling you is something that I mentioned at the beginning, which is that the K theory of the sphere spectrum is mixing information from TC of S, which is familiar objects from topology, with information from K of Z, which is arithmetic. And so the reason that this thing has chromatic convergence is a mix of sort of a familiar topological reason, which is the input from TC of S, and the Wholem-Lichtenbaum conjecture, which is input from or what we understand about K of Z. So I don't know what else to say about that, but it's sort of an interesting thing. Or that interplay is very rich, maybe is all what I want to emphasize. Okay. So what about the non-connective piece of all of this? So for the non-connective part of this uses work that I did with Mike Mandel, where we understand as much as you can without resolving some unsolved conjectures in number theory about the homotopy, about the homotopy type of the K theory of the sphere spectrum in terms of arithmetic duality. And let me say a little bit about what's going on with that. So here, arithmetic duality means some kind of spectral lift of Tate-Patu duality. And, what we're going to do is, if we write f of r for the homotopy fiber of the map from R to its chromatic completion, then the Dundas-McCarthy-Goodwillie square basically tells us that f of the sphere spectrum, so this non-connective stuff, is related to is f of the fiber of the cyclotomic trace from K of Z to TC of Z. So that's basically what we have to study. But that's also what comes up. That's exactly what happens in the strategy for this arithmetic duality work, where the point is that square tells you that the homotopy fiber of the map from K of S to TC of S is equivalent to the homotopy fiber of the map from K of Z to TC of Z. And now computations of Hessel, Holt, Madsen tell you that homotopy fiber is equivalent to the homotopy fiber of the completion map in K theory, going from from the P completion of the K theory of the integers to the P completion of the K theory of the p-adics. And and I should mention one thing here, which is that this is an area where K-theory, I mean, you know this, but maybe I say it anyway. This is an area where K-theory is very different from TC, right? That map is an equivalence on TC. But in K-theory, it's not. And that's that, you know, that distinction, that's a key distinction. And so you, and really, maybe just to say a little bit more, really what happens then is that by Quillen's localization theorem, this is the same as the fiber of this map. And this admits an interpretation by Thomason's work in terms of a tall cohomology. And that completion map sits in the Tate-Patu duality sequence. And that's where you replace all these K groups by suitable atol cohomology groups. And that's ultimately what maybe guides you to think that arithmetic duality should hold on the spectrum level. And I should say that this program for understanding the K theory of the sphere spectrum computationally was sort of initiated by John Rognus, the strategy of reducing to Tate-Patu duality. John worked this out at regular primes. And then, the content of what Mike and I did was to work it out at all primes. And so now what we show is that at P, there's an Anderson duality pairing between the K1 localization of K of Z and the K1, a shift of the K1 localization of the fiber of the cyclotomic trace map. And we know some things about the connecting maps, although maybe less than you would like. And where does this come from? This pairing there are two parts to it. It's induced by the module action. So the fiber, Hophi of K of Z to TC of Z is a module over K of Z in the evident way. And you have that action, and then you have a specific map on pi minus 1 of the K1 localization of the fiber with coefficients in Q mod Z or in Z mod P infinity equivalently. And by coefficients, I just mean smash with the Moore spectrum. And that map, we take a certain map to Q mod Z, and that map basically is coming from the Albert Brouwer-Hassan-Noether theorem. And this is this key arithmetic input into constructing this pairing. But so what we get from this now is the strategy of proof, coming back to this chromatic convergence question. The strategy of proof that we're interested in is to produce from this an induced pairing between the P completion of the K theory of Z and the shift by 2 of this fiber of the chromatic completion map on the fiber of the cyclotomic trace. That's a bit of a mouthful, but that's what we do. And you can write down, I guess I'm not going to do it, but you can, if you look at the pairing, the arithmetic pairing for the fiber of the cyclotomic trace, it's not too hard to write down a candidate for what this thing should be, what the pairing maps inducing the duality is. But the strategy of verification is kind of interesting, and I want to say a little bit about it. So to actually check that it works, that it really does give you this Anderson duality pairing, we end up having to use the so-called Eigen Splittings of K1 of K of Z and LK1 of the fiber. And these, what do these Eigen Splittings come from? So one of the, let me move this down slightly. One of the sort of great triumphs of computation of algebraic K theory of rings of integers was work of Dwyer Mitchell, who observed that you can study the K theory of the K1 localization of sorry, the K1 localization of the K theory of a ring of integers in terms of Iwasawa theory. And this is because of this, this is worth advertising. This is because of this magical thing that the operations on p-adic Ku is basically the Iwasawa algebra. And so, and then that combined with work of Bousfield basically tells you that that category is very close, the category of K1 local things is very close to being algebraic. And what they really do is that they prove that the K theory of the K1 localization of the K theory of a ring of integers is a Moore spectrum in that category. And the algebraic data is a well-known standard Iwasawa module. And so what they get out of that is they get these splittings where these things split up into pieces. And the pieces have a term that looks like the periodic J spectrum. And then they have a term that looks like, in K of Z is J wedge some stuff. And so this is what you expect. And then they have a term, they have a series of terms. And these things, these Y zeros, these are fibers of maps from shifts of the atom's summand to itself. And those, and this is where, the way this is sewn together is that those maps from, shifts of L to L, their coefficients are related to values of p-adic L functions that come out of Iwasawa theory. So this is sort of, when you start to go down the road of trying to understand the interaction between number theory and algebraic K theory, it's mediated at the level of homotopy types. It's mediated by the fact that the very construction of these pieces of K theory, at least after K1 localization, but remember by the Cohen-Lichtenbaum conjecture, that's fine. We don't do any violence by doing that, encode the data of the p-adic L functions. And one of the things that we prove is that Anderson duality mixes these things up. So I think I didn't write it down, and so I'll probably get it wrong, but it's something like yi, maybe I won't write to avoid writing something false on the slide, but it's something like yi is paired with x of p minus I, except at one of the ends. But there's a transposition relationship that tells you how Anderson duality swaps these things. And so if you look at that, you can use that to verify that the candidate pairing on, let's get another color, that the candidate pairing here is actually the right thing. And that's sort of the strategy of proof for that. Now, one of the really interesting things about this, which I want to advertise as an aside, is that these splittings, we refer to these as Eigen Splittings. And one of the, and they come from Eigen Splittings associated to the Teichmuller character. But one of the things about them that is cool is that this is exactly the splitting you would get if there were Adams operations on K of S. And those Adams operations were compatible in the ways you would hope with the known Adams operations on K of Z and TC of S, and with the Dundas-McCarthy square, Dundas-McCarthy-Goodwillie square. So as far as I know, we don't have sufficiently rigid Adams operations on the K theory of the sphere spectrum, or really anything, like that. But we ought to, because this is telling us that they ought to be there. And, so I think maybe one thing to say is that as I understand it, there's very nice recent work, or at least recently posted work of Matthew and Nikolaus and Clark Barwick and maybe someone else whose name I'm forgetting, and I sincerely apologize for that, on sort of a functoriality of K theory and polynomial functors, which gives you a way to think about Adams operations. But as I understand it, the problem is for Adams operations, you need something like an exterior power functor on your module category, and we sort of don't know what that's supposed to be for things that look like K of S. It looks like S. Okay, so that brings us to the end of the structured part of the talk. But since I have a little bit of time, I want to say a few more things about this story. So one question you could ask is, well, let me just give you this recap of the structure of the proof. So we show that that the K theory is a wedge summand of the inverse limit of the finite localizations, K theory of the finite localizations of the sphere, basically by using the fact that K theory has chromatic convergence when you complete on the outside, and the work of Land, Matthew, Meyer, Tam to understand how to move K theory telescopic localizations inside and outside of K theory. Right, that's the key structure. And then there's a bunch of stuff to actually make that work. Now, one other question you might wonder about, so you could ask the following question. What about the map K of S? Or maybe let's write this like this to, oops, what about the map? Where now I'm using the chromatic, not the finite localizations, but the chromatic localizations. So what about this? And this is not, on the one hand, this is not particularly closely related. This question is not particularly closely related to the redshift perspective, right? It's not sort of the right tower for that, unless the telescope conjecture is true. On the other hand, it would be interesting to know. One of the reasons I think it would be interesting to know is that, if you think about how to prove this, right, you are often inexorably led to consider questions about the relationship. I don't know. This is what I thought about. Inexorably led is maybe too strong. A natural thing that some people might ask is, what is the relationship between Perf of SP and Wholem of Perf of LNS? Right? You could ask about a question like this, and what you find is that, of course, this embeds in here. But there's all this other stuff, right? This has lots of other garbage, and the kind of examples that one thinks about are games where you, what does this look like? You can make this by thinking about sort of towers where at any given level it's finite, and each time you wedge on a type n thing, and you keep, as n goes higher and higher, and now that's going to look finite at any stage, so it's always in perf LNS, but it isn't in the limit. And this is related to questions about, sort of the behavior of this chromatic completion. So understanding this, I think, would be structurally interesting. And I don't, so what to say about that? You can try to run the kinds of arguments that I was describing earlier so it might be too much to ask for this to be an equivalence, but you can ask, sort of a version of what we proved. You might ask, is K of SP to Wholem K of LNS, is this, inclusion of a wedge summand? That might leave you agnostic about what happens to the sort of schmutz that seems to turn up in this, right? You might conjecture that stuff is 0 on K theory, or you might not. And you can run most of the argument I describe. But in a sort of interesting, albeit kind of frustrating turn of events, there's a key issue in verifying the arithmetic patching argument. We do this sort of, at P and Q, and we glue these things together to get the splitting map ultimately. And there's one place in the patching argument where you have to know that two maps are really the same, and we just don't. So maybe we can figure it out. Maybe if you read our paper where this is kind of discussed, you can figure it out. But anyway, there's a small gap that makes it the case that we aren't sure whether or not it looks likely to me. I mean, those maps, morally, it feels like those maps should be the same, but but who knows? And so, but it seems like this is probably true. This is a wedge summand, and I don't know whether it's reasonable to expect anything stronger. So yeah, I think that's probably a good place for me to stop talking. So I will stop, except and to answer questions.